Hello, 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 hello. Welcome back to Mr. Visca's AP Calculus AB. Review course. Okay, we are going to review Unit 6, which are differential equations and math modeling. And these are the notes that review that unit. These are not the notes for every single thing in the unit. If you are looking for Unit 6 Day 1, Unit 6 Day 2 in my AP Calculus AB course, well, you will have to search for Unit 6 Day 1 and Unit 6 Day 2, etc., etc. This is review of the entire unit. Okay, this is part 1 of the videos. Let's get started, shall we? Now, slope fields. I don't like slope fields, not because they're difficult, but I like calculating things. I like equations. I like going crazy with things. And this to me seems a little bit elementary, if you will. So here's what a slope field of y prime equals 2x looks like. Why is it called a slope field? Because a derivative is the same thing as a slope. Remember? You should at this point. Now, here's what we do here. Okay, we take all these points that we're giving. Okay, here's the origin right here. This is the point 1, 0. Okay, this is the point 2, 0, and so forth. This is the point 0, 1. This is the point 0, 2, and so forth. Negative 1, 0. This is negative 1, positive 1. This is 1, 1. I think you get the picture. And what I do here is I take my coordinates. So for right now, let's take a look at the origin. That is the point 0, 0. And I plug those variables into my derivative. In this case, the y value doesn't make a big hootenanny difference. How come? Because my slope or derivative is 2 times x. There is no y. So really, only this column is going to come into play. We've learned, though, we can have derivatives equal something like 2y minus x. We could do that, where then I would use both columns. But in this case, I really don't need the y's. The only thing the y is telling me is where the slope I'm coming up with, where that little line that's going to represent that slope is going to go. What coordinate exactly? So if I throw a 0 in at any time into my derivative, it will be 2 times 0. So it will always be a horizontal line. So anytime, okay, anytime I have a coordinate where the x is 0, right here, right here, right here, right here, right here, the slope is going to be 0. And the slope, 0 is a horizontal line. So that's why we see all horizontal lines going through any coordinate that has a 0. So what about any coordinate where my x is 1? Well, 2 times 1 is 2. So my derivative for any point where x is 1, this coordinate here, 1. This coordinate here, x is 1. This coordinate here, x is 1. And these lines I'm drawing are a slope of 2. Okay? So any time by that 2. What about when x is 2? Okay, that's right here. The slope should be 4. So it should be slightly steeper than the ones I just drew, and so forth. What about its negative 1? Well, when x is negative 1, my calculation for my slope, 2 times negative 1, is negative 2, okay? It's the same as these things I just drew. Do this in a different highlight. It's the same thing as this one, except it is negative version of it, okay? So anytime x is negative 1, and so forth, when x is negative 2, it's the same thing we did here, okay? Instead of having a positive 4, my slope will be negative 4. Okay, and I just fill in every coordinate that they give me. That is the gist of the review of slope fields. On to our next problem, where we don't have a table created for us. We are going to create a table. Now, I'm going to put on my table, okay, I have x's, I have my y's, so I'm going to do this. And I've got to list all these coordinates, okay? So let's start here. Negative 1. When x is negative 1, it happens at 3 spots, right? Negative 1x, negative 1x, negative 1x. It happens negative 1, 0, when y is 0. Negative 1 when y is positive 1. And x is negative 1 when y is positive 2. All right? Next, I have these 3 points. when x is 1. Okay? X is a positive 1 when y is 0, when y is 1, and when y is 2. So, when y is 0, y is 1, and y is 2. And last, certainly not least, we have these 3 points when x is 2. So 2, 2, 2. And that happens when y is 0, y is 1, y is 2. So all I have done to this point is just create the table. But I need to find the slope at all of these points. Visca, how come there are no dots where x is 0? Meaning you're asking me about this point here, here, and here. Well, there's no points here. Okay, on a test, and this really is left out of the question, it normally says create a slope field for the points given. And anywhere there's a dot, there's a point given. Trust me, if they wanted you to do that, and if you wanted to, because you know what, I'm a little bit, OCD, I want them there, we can do that if we really wanted to. But for right now, let's stick with the problem, okay? Okay, now I need to know the slope at each one of these points, okay? The slope, or the derivative, is 3 times x plus whatever y is. So for all of these, okay, I hate to do lines here to separate them, but I'm going to go through and do all this here. All right, just so that we keep things nice and fresh and clean and healthy and smart. Okay, so if I take a -1 and put it in for x, I get -3 plus 0. Well, my slope of that coordinate is -3. Okay. Now, anytime I multiply 3 by a -1, it'll be -3 plus my y. So -3 plus 1 gives me -2. -3 plus 2 gives me -1. All right? We found our first slopes. Now, I need to put an x value in of 1. Anytime I multiply 3 times 1, I'm going to get 3, and I need to add the y value. So 3 plus 0 is 3. 3 plus 1 is 4. 3 plus 2 is 5. All right? Now we'll do the last set of coordinates. And in case you think I'm going fast, or you're like, how is he coming up with these numbers? I'm taking an x of 2 and a y of 0 and plugging it x is 2, y is 0. 3 times 2 is 6 plus 0, 6. 3 times 2, 6 plus 1 is 7. 3 times 2 is 6 plus 2 is 8. All right, I'm going to represent all of these. Okay, I'm going to get rid of these little visuals that I use to create our table here. I need to put a slope. Let's start at my -1. When x is -1 and y is 0, I get a slope of -3. So it's going to be negative, I don't know, something like that, 3. Now, you might say, like, Visca, how are they going to know? I'm going to tell you something. This slope is negative and steep. This one is not as steep. This one is definitely less steep than the previous. So -1, I know, should look like this. -2 should be a little bit steeper. Boom, -3 should be even a little bit steeper. All right? How do I know that this is -1? Because if I extend this, it's down 1 over 1 to the next point. Okay? So we can do that and then kind of gauge the rest of your slopes off of that first drawing, if you will. As long as you have an idea. Look, this should be, and you don't have to write this on your graph, this should have a slope of -3. This should have a slope of -2. This should have a slope of -1. So as long as I get steeper as I draw these, I'm okay. All right? That shows to someone in calculus that you know what you're doing. Now, if you draw a slope of -2 that looks like this, yeah, that's they're going to mark off for, okay? Now, keep in mind, we still need to do 6 other points. We just drew these 3 slopes. Now, look it. I'm going to draw this, which is 3. I don't know, maybe it looks like that. But keep in mind, these are going to get steeper and steeper as I go. So don't draw 3 too steep, because then it's going to be crazy. So I've got at 1, 0, it's a slope of 3. 4, it's a little steeper. 5, it's a little steeper. 6, it's a little steeper. 7, it's a little steeper. 8, it's even a little bit steeper like that. Okay? And we just did these points right there. Boom. Perfect slope field. No, let's not attack this. You know what? Go ahead. Do the zeros right now. Pause this video And what if we had 3 points right here for the same situation? Okay, let's say we had those points to graph. We have 3 coordinates, okay, when x is 0. 1, 2, 3. That's when y is 0, when y is 1, and when y is 2. I need to find the derivatives of those, okay? So anytime I plug a 0 in for x, 3 times 0 is 0. So 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 2 is 2. Those would be the slopes of the 3 dots we just created. So 0, 0 has a horizontal slope, okay? At 0, 1, I have a slope of 1. So, I don't know, it kind of looks like that. At 0, 2, I have a slope of 2. It kind of looks like that, okay? So if I wanted to do those points, there they are. I know some people, and maybe myself included, a little bit OCD, is like, hey, it doesn't go all the way across, but that's fine. Okay, we just created those ourselves, and that's how you do slope fields. All right, perfect. To see or not to see? That's, my friends, is the question when it comes to integrals. Now, we've talked about this before, okay, in Unit 5 review, whether we need to see or not. For an indefinite integral, we will always need a c. We always need to put plus c at the end, okay, because we have no bounds. Whenever we have bounds, that means it does not require the c. Not a c. Okay, plus c. So let's go ahead and do these 2 things here just quickly. I'm going to use the reverse power rule, so I'm going to add 1, then divide by that number, okay? Now, since there are no bounds, my answer has to be plus c. This is my answer. Simple. Now, I'm going to do the same thing over here. It is the same function that I'm integrating, so it's still x cubed over 3. But this time I have bounds. I want that from 4 to 1, okay? So I need to plug in my upper bound first into x. So it is 4 cubed over 3. Then I got to take that value and subtract, throwing the lower bound in there. So it is 1 cubed over 3. So I find out what those 2 values are and I subtract them. And if I do my math right, okay, that's 64 over 3 minus 1 over 3. That gives us a total of 63 over 3. You better not leave that like that, because 3 goes into 63 perfect 21 times. So who remembers what integration represents? Area under the curve. The area under the curve of x squared from the bounds 4 to 1 is 21. All right? Not too shabby. I know we talked about U sub and integration, but I'd like to do a little bit more of that here because it's an important part of integrating, okay, able to do U substitution. So right now, I'm looking at this, the integration of x plus 2 to the power of 5. I could take x plus 2 and multiply it times itself 5 times. I would probably use Pascal's triangle to do that, and I could. And I'll get some polynomial, x to the 5th, x to the 4th, something, plus or minus x to the 3rd, so forth. And I could then take the power rule, reverse power rule, for each one of these individually. And trust me, some kids that forget how to do U sub for a moment, they'll do that. They'll spend all that time. That's a lot of time. Or, okay, or I could say to myself, well, how would this become easier using U? Okay, as a substitution. If I just integrated u to the power of 5, that's easy. That's just a reverse power rule. But here's where a lot of children, okay, here's the stump. Here's the problem. Some people struggle with this. Some people don't. How do I know what to make my u? Well, when you say it, Visca, it seems obvious. But how do I know what to make my u? I need to be sure that whatever my u is, okay, in this case, I'm looking at x, but I'm going to make it x plus 2. that the derivative of x plus 2 also needs to be there. Okay? So, meaning, if I make u x plus 2, what's the derivative of that? Well, it's just 1 dx. We always put dx anytime we take the derivative with u substitution, okay? So here's my 1 dx. It's there. Here's that, okay? It's good. So I integrate. I make my x plus 2 a u. It's still to the power of 5, right? And then for my 1 dx, well, 1 dx equals du. Now I can integrate this a million times easier. Power rule. Reverse it. Back it up. U to the 6 divided by 6. There are no bounds. That means I always need to put plus c. Now, because there are no bounds, I don't know if you remember or if you saw from the Unit 5 review, I would also have to do my u substitution for my bounds, okay? And it would be a lot easier to calculate the number here, all right? But there are no bounds, so my answer isn't going to be a number, it's going to be an expression. If my answer is an expression, I need to put the x back in, okay? So this has got to go back in for my u right here. And for the u is x plus 2. That's to the power of 6 divided by 6 plus c. Bang, chitty, bang, bang, chitty, chitty, bang, bang, done. Good. Let's do another one, okay? Let's do another one. And if you want to pause this and look at this for a moment and try it, I mean, you should be doing that in all these videos. A lot of people just write down the notes. It drives me crazy. But you should be trying to do these and pausing these. At the very least, pause it and look at it. And if not, write it down, like kind of think what you would have done. And if it was right, like if you figure out what u and du should have been, then you should have went ahead and tried this on your own. I mean, that's how you know that you know it. So let's start. I need to find a u and I need to find a du because this would be a nightmare to integrate otherwise. Now, remember what I said. I need to find an expression, but its derivative also needs to be there. Okay, so I'm going to do this. No, I don't want a crayon. Well, I do, but not for this purpose. The derivative of x squared is 2x dx. So I can make x squared my u, but I want to make it x squared plus 1. How come? Because the derivative, and you don't have to write this part down right this second, the derivative of 1 plus x squared and the derivative of just x squared, it's both the same thing, 2x. So if I'm going to substitute stuff out, why don't I take more stuff out and make it easier for myself? You should always do that, okay? So, because a lot of kids will just put a u in for x squared. And that still becomes a little bit of a problem. It becomes easier when I make the whole thing my u. How come? How come I can make more my u? Because the derivative is still 2x dx. The derivative of this is still 2x dx. So when we substitute in, we're still getting rid of everything. So integrate the square root. This is now u. And this whole thing, not just a dx, but 2x dx gets substituted for du. All right? Now, we love our reverse power rule. So I'm going to create an exponent here. Okay, I'm going to rewrite this so that's the integration of u to the 1/2. Please, I can't tell you the number of times in calculus square root is the same thing as exponent 1/2. In the calculator, if I did the square root of 4, that'll equal the same thing as if I did an exponent of 1/2. Or an exponent, because some of you guys are freaked out about decimals, of 0.5. Okay, it's the same thing. So why am I doing that? Because working with exponents is a million times easier when we integrate and take derivatives. All right, so the same rules apply. I add 1 to the exponent, so I have u 1/2 plus 1. Well, 1 is the same thing as saying 2 over 2. So really, that's u to the 3/2. When I add these, that's 3 over 2. Now, I got to divide by that. What I tell my students is I skip this step right here, and I go right to this. How come? Because dividing by a fraction is the same thing as multiplying by its reciprocal. Okay? So we don't even write, we'll write this, but we don't even write this part below. They go right to here. And I say it every time. Say dividing by that fraction is the same thing as multiplying by its reciprocal. So let's take this and apply it. So I'm going to integrate this. If I add 1 to the exponent and divide by that, I get 2 thirds u to the 3 halves. Are there bounds? No, there are not. So I always need to have a plus c. Is my answer an expression? It is an expression, so I need to put my x back in. Okay? So that is 1 plus x squared. So I've got 2 thirds times 1 plus x squared to 3 halves plus c. Now, this is great. If it's short answer, that's fine. There are multiple ways, if this was a multiple choice problem, that this could be written. Okay? So first of all, I could turn my fraction exponent back into a radical. So I can have 2 thirds times radical. Top comes down, right? I have 1 plus x squared in here. Top comes down, bottom flies out. So it's the square root of 1 plus x squared cubed. Now, if it's a square root, we really don't got to write it, do we? Well, get rid of that 2. Where's the 2? There it is. We really don't have to write that 2 there. All right? Plus c. You can write it like that. Or they can put this in the numerator with the 2. They can say 2 times the square root of 1 plus x squared, all cubed. Okay? That's all over 3 plus c. Okay? You can do it like that as well. So if it's multiple choice, just know that if you come up with this and don't see it in multiple choice listing, maybe it's written like this, maybe it's written like this, I don't know. But the one thing, if it's short answer, don't go crazy trying to simplify or change it if you already have the right answer. Okay? Good, we're doing good at the 22-minute mark. Fantastic. All right, so we have 4 more problems to do that do not have bounds. Let's try and get through those in 8 minutes. And if we go a little bit over, we'll go over because we just stop right when we bring the bounds back in, okay, when we don't need to put the plus c. All right, so let's take a look at this one here. All right, man, this next one's tough. What do I make the integration? All right, so I have been saying that whatever we make u, the du needs to be there. If the du is not there, at least part of the du needs to be there, meaning I should be able to take out, there should be no more variables. Okay? If I have an extra number flying around there, that's good, and I will show you what I mean in a moment. Okay? So, all right, if I take the derivative of 4x minus 1, okay, if I make this my u, okay, so it's 4x minus 1. What's the derivative of that? It's 4. There's no more variable. 4, and then we always write dx. I'm going to take that. Do you want to know why? Because when I substitute in for my dx, okay, when I substitute in for this, I got to get dx alone over here. Okay, and this alone over here. So look at the little equation I have. I actually have a little bit of an equation right here. How do I get my dx alone? Don't I divide by 4? What I do to one side, I do to the other? So I technically have 1/4 du equals dx. So this is going in for u, and I'm not going to put du in for dx. I'm going to put 1/4 du in for dx. So when I say, when you substitute in, okay, and I can put a number in with a du, but I can't put a variable. If that was 1/4 x in for, you know, I can't have a variable on the left side. When I get dx alone, it should equal something that doesn't have a variable, or that will leave a variable in my equation, okay? I don't want anything that'll leave a variable in my equation for my derivative, okay? Does that make sense? This should not have a variable in it. Everything should be substituted out over here with a variable, all right? Let me explain. Ready? I'm going to integrate the square root 4x minus 1 is u. Now, n for dx is not du, it's 1/4 du, okay? And what do our rules about constants say? We can take a constant out, we can integrate, and then multiply the constant back in. So it is 1/4 times the integration. I'm going to change my square root sign to an exponent. Now this is pretty much what we just did, okay, except we're multiplying by 1/4. So what do I do here? Let's integrate this. I add 1 to my exponent, and that's u to the 3/2. When I divide by 3/2, that's like multiplying by the reciprocal, 2/3 plus c, okay? Now, I still need to multiply by 1/4, all right? So if I finish this problem out, 1 times 2, 2 goes into 4 twice. So I get 1 over 2 times 3. It's 1/6 times u to the 3/2 plus c. There's a c here. There are no bounds. I need an expression in my answer, which means I need an x in my answer. So I'm going to put 4x minus 1 back in for u. So I've got 1/6 times 4x minus 1 to the 3/2 plus c. I just showed you how you can change this back if you want to, so I'm not going to show you again. That is a great answer. Okay? So the big thing you need to realize here is if the derivative isn't there in its entirety, it's fine as long as you have a constant with your du when you solve here. Okay? As long as this side gets substituted out. You see the dx goes bye-bye, right? The variable should still go bye-bye. But if you have to bring a number back to this side, that's fine. You can put a number in. You just don't want to put another variable back in for it. So let's move on to the next one, shall we? We shall. Okay, big line, draw right there in the middle. All right. All right, so what can I make my u so that my derivative, or at least will be the derivative with either a number, there won't be any variables left. A variable would need to stay with the dx. So, this is what I'm going to do. I'm going to make u 7x plus 5. Okay? 7x plus 5 because the derivative is 7 dx. All right? 7 dx. So I don't have a 7 dx to substitute in for. I just need to get dx alone here. So I'm going to divide this side by 7, divide this by 7, and say 1/7 du is going to go in for my dx. Good. I'm good because there's only a number on this side. Good. This is u. This is what dx is going to be substituted out for, 1/7 du. So let me rewrite. My integral, it's the cosine of u times 1/7 du. Constant, bring it out. In fact, my students are so well trained in this. They don't even write this step here. When they write it, knowing there's a constant here, they write it just like this. The 1/7 is on the outside. Now, this is not an exponent rule or a reverse exponent rule. This right here is trig. You need to know your trig. So this is reverse of derivative. What do I take the derivative of that would give me cosine? The derivative of sine is cosine. So again, integration is the opposite of derivative. So instead of moving this way, we're moving back this way. Okay, so the integration of cosine of u is sine of u. Are there bounds? No, there are not. And don't forget, we still got to multiply times my 1/7. All right? My answer is an expression, so guess what? I need an expression back in. So 7x plus 5, that is going to go back in for my u. So it's 1/7 sine of 7x plus 5 plus c. If you want to multiply these two together, I can write it like this over 7. That's fine, but you don't need to. If it's short answer, you can leave it like that. That is a very bad 7. There you go. That's good. Super. Okay, two more. Let's do these. Oh, these are two great problems. This brings the substituting in for du dx to a whole new level here. All right? So I've got to find a u and also have the derivative of u there. So if I make x cubed u, okay, let's do that now. So if u equals x cubed, the derivative of u, there is x squared in the derivative of u. Okay, there is x squared, and then the dx will be in there. So the derivative of u is 3x squared dx. So really, remember, I can have a number on the left side. I just don't want a variable there. So I'm going to substitute this out for u, but I'm going to take x squared dx out. So I'm going to take x squared dx out, which means this 3 has got to come to the other side. So I'm going to divide this side by 3 and this side by 3. So 1/3 du equals x squared dx. Oh, this is great. Before I substitute, let me rewrite this integral. I've got the integral. I'm going to put the sine of x cubed times x squared dx. Okay, so now is it a little bit more obvious? In for my x cubed is going to be a u. And in for x squared dx, I'm going to put 1/3 du. My 1/3 goes on the outside. It's a constant. Du. That's it. Again, remember, numbers can be here. As long as your variables get substituted out, you're fine. You are fine. All right? So what's the derivative of x cubed? Well, it's 3x squared. So I know the 3 is going to kind of come back into play here, right? So that's going to come back in by the 1/3. But the x squared pops out. All right? So let's integrate this. Okay. Be careful here. This is trig. It is reverse derivative. So what do I take the derivative of that would give me sine of u? Well, in this case, we could do x, whatever. Well, cosine of x is almost, that gives me negative sine. Okay, well, if I negate the right side, I negate the left side. Okay, so the derivative of negative cosine of x, ooh, yeah, would give me a positive sine of x, all right? Make sense? Should be. Let me do that. Let me explain that one better way, okay? The derivative of cosine of x is negative sine of x. But I want a positive sine of x here, right? So if I multiply this by -1, what I do to one side, I got to do this. So the derivative of negative cosine of x would give you a positive sine of x, okay? So when I integrate this, I get negative cosine of u, there's no bounds, plus c, times 1/3. So there's an expression. So I need an x. My x cubed has got to come back in for my u. I'll make this negative 1/3 cosine of x cubed plus c. Done and done. All right? One more left. I know we're a few minutes over 30 minutes. I know you're tired. Your brain hurts. But we're going to do this one because this next one is great. It's gravy. Gravy. Bam. All right. Now, I need a u and I need a du. All right? So right now, I always tell my students, this means I'm taking the sine of x to the power of 4. So I'm going to write that as sine of x, the whole thing to the power of 4, cosine of x dx. Right now, if this doesn't pop out to you, you don't know your trig derivatives. The derivative of sine is cosine. So I'm going to make u sine of x, and the derivative of u is cosine of x dx. I don't have to move anything around, because in for my sine of x, I'm going to make that a u to the power of 4. My cosine of x dx is completely getting substituted out for du. Oh, man. Reverse power rule. Love it. I get u to the power of 5 over 5 plus c. There's an expression left, not a number because there are no bounds, which means I need my expression back in for u. So I'm going to say sine of x to the power of 5 over 5 plus c. That is absolutely mathematically and algebraically correct, but if this was multiple choice, they would still put the exponent back in the middle. Okay? And when you write your answer, I mean, that's like writing a quadratic in standard form. Okay, and this is like writing your trig in the appropriate form. Okay, so I expect my kids to do that. If they do this, is it wrong? No. But the more they make the connection between these two, the more this isn't going to throw them off right here. I'm sorry, that's not going to throw them off. So we're done. Like, comments, ring the bell. Do whatever you want. But I think we're only going to need one more video to get through the rest of Unit 6 review. Oh, man, we still got to do this U sub with bounds, which is going to be cool. And we also have to do separable differentiation. Oh, that's great. Or excuse me, separable, it's integration, separate. And you know what? I'm going to just, hold on one second. Okay, it's separable differential equations because they're derivatives and we're going backwards. We've got to integrate the differential equations, but do it separately. So it's, even though we're doing integration, we're working on separable differential equations because we're going backwards. You'll see on part 2 video, okay? I'll see you then. Ring-a-ding-ding that bell. See ya.